Okay, so last time let f in K be an inclusion of fields. Then we introduced a bit of terminology last time, and we said that K was a field extension of F. So we say K is a field extension of F. And we write this as K over F. So the other thing we talked about last time was the degree of a field extension. So suppose that K is a field extension of F, then in that case you can consider K to be an F module by just restricting the multiplication from elements of K to elements of F. So we can multiply any element in K by any element in F, and that makes K into an F module, but F is a field, so an F module is the same thing as a vector space over F, and so in this way we can consider K as a vector space over F, and doing this we can define the degree of K over F to be the dimension of the vector space K when it's considered as a vector space over F. So we can consider K as a vector space over F, and then the degree of K over F is defined to be the dimension of K as an F vector space. So this is the degree of K over F. Okay, and at the end of the lecture, we started investigating the field fx quotiented by the ideal px, where px in fx is irreducible. And in particular, we looked at some examples last time. So for example, we constructed the complex numbers as Rx quotiented out by the ideal generated by the polynomial x squared plus 1. Okay, so for much of today's lecture, we're also going to study this particular field, fx quotiented by an irreducible polynomial. Okay. So to begin with, let's remark that we have, for any field f, we have, of course, a natural inclusion of f into the ring of polynomials with coefficients in f, which just sends a constant to the constant polynomial. Okay, but we can now compose this with the quotient homomorphism taking the ring of polynomials to the field fx quotiented by px, where p is irreducible as before. So this is just, of course, the quotient homomorphism taking, say, fx to fx bar. So now we can compose these two homomorphisms, the inclusion of f into fx with the quotient, to get a field homomorphism f. So putting these two homomorphisms together, one after the other, we get a field homomorphism from the field f to the field given by quotienting fx by the ideal generated by an irreducible polynomial. And this is nothing more than c goes to the representative of c for a constant c in f. Okay, so let's start with a simple lemma. Lemma: the natural field homomorphism f to fx quotiented by px with px irreducible given by c goes to the representative of c is injective. So this lemma tells us that we have a natural inclusion from the field of the field f into the field fx over px. Okay, proof. Well, we proved last time that non-zero field homomorphisms are automatically injective. So we only have to prove that this given field homomorphism is non-zero. Is non-zero, but well, 1 isn't 0. So the class of 1 gets sent to a non-zero point. So it's enough to observe that 1 bar, which is the image of 1, is not 0. Because if 1 was 0, then the field fx quotiented by px would be 0, which would mean that px was a unit, but by definition, irreducible elements are not units. So this is not 0, because if that was 0, then fx over px would just be 0, which first of all would mean it's not a field, because by definition fields have at least two elements. 0 has to be different to 1. And this is reflected in the fact that P is irreducible, and irreducible elements can't be units. As by definition, irreducible elements are non-units. Okay, so the natural field homomorphism is injective. And then in particular, we can consider the field fx over px as a field extension of f. So by the above, we can consider, since f is an inclusion into fx over px, then we can consider this field as a field extension of f, where I'm identifying f really with its image in fx over px, which is okay since the homomorphism is injective. So identifying here f with its image Okay, so this field that we've just constructed is a field extension of f. And then the natural question you might want to ask is, what is the degree of this field extension? What is the degree of the field extension fx over px over f, where px is irreducible. Okay, so the answer to this natural question is given by the following theorem. So let px be irreducible, and now set K to be the field that we get by taking the quotient of fx by the px. Then let theta be defined to be the equivalence class of x in K. And let n be the degree of the irreducible polynomial px. Then the claim is that 1 theta theta squared up to theta n minus 1 provides us with a basis for the field K over F. And in particular, this gives us that the degree of K over F equals F, because we have n elements in the basis. Okay. So here's a statement telling us that the degree of this field extension we've just constructed is given by the degree of the polynomial px. So this maybe can be considered as good motivation for the terminology degree. At least in this case, degree of the field extension is the same thing as degree of the polynomial. Okay, proof. So take some polynomial ax in the polynomial ring fx. Then we can apply the division algorithm for polynomials. So applying the division algorithm for polynomials, we can divide by px, and we can get that ax equals qx px plus rx for polynomials in fx, where the degree of rx, if it's non-zero, is less than p, with either rx equals 0 or degree of rx less than the degree of px. But px is sent to 0 when we quotient by the ideal of px. So taking equivalence classes in the field K, we get that the equivalence class of A equals the equivalence class of R in the field K. But observe that the degree of px was by definition n. So this tells us that any element, any polynomial a in fx is equivalent to some polynomial of degree strictly less than n in k. So in particular, any element in K is represented by a polynomial of degree less than or equal to n minus 1. So any element in K is represented by a polynomial of degree less than or equal to n minus 1, because we've just shown that the division algorithm gives us that immediately. Okay, so if we go back to our definition of theta as the equivalence class of x, then we've just shown that any element is represented by polynomials of degree less than or equal to n minus 1. But since theta is the equivalence class of x, taking all the powers of theta gives us the equivalence classes of 1, x squared, up to x n minus 1, and the span of these is all polynomials less than or equal to n minus 1, and any element is represented by such a polynomial. So this tells us that the set that we want to be a basis at least spans K as an F vector space. Okay, so what we've just said implies that 1x squared x n minus 1 equals 1 theta to the n minus 1 spans K over F, because clearly the span of 1x squared up to x n minus 1 is equivalence classes of polynomials of degree less than or equal to n minus 1, and any element in K is represented by such a polynomial. Okay, so it remains to prove so we've shown now that 1 theta up to theta n minus 1 spans K, and in order for this to be a basis, it just remains to prove that 1 theta up to theta n minus 1 is a linearly independent set. So suppose that we have some linear combination lambda naught plus lambda 1 theta plus lambda 2 theta squared plus lambda n minus 1 theta n minus 1 equals 0 in K, where the coefficients lie in the field F. Then what we need to prove to show that this set is a linearly independent set, we need to prove that the coefficients lambda naught, lambda 1, and so on are all equal to 0. Okay, so let's first rewrite this. So by definition, theta is the equivalence class of x. So what we have above is the same thing as this, replacing the thetas with x's. Let's write it like this, equals 0 bar in fx over px. And this is exactly the same as saying, by definition of the equivalence classes, this is the same as saying lambda naught plus lambda 1 x, and so on, lies in the ideal P of x. Okay, but don't forget that this guy had degree n, and therefore any non-zero element in the ideal of P has degree greater than n. So all elements in the ideal of P, they have to be multiples of P, and therefore their degrees have to be multiples of n, and any multiple of n is greater than n, obviously, with the exception of 0, because the degree is of course positive. But we've just got some polynomial here, lambda naught plus lambda 1x, and so on, lambda n minus 1, xn minus 1, in the ideal of P. Since its degree is n minus 1, or its degree is at most n minus 1, then for it to land in Px, it must have degree 0. It must be, so it must actually be the 0 polynomial, because anything in the ideal of Px has degree some multiple of n, and P is not constant because it's irreducible, can't be a unit. So the only way for it to have degree less than n and be a multiple of P is if it's actually 0. Okay, so since this expression has degree less than or equal to n minus 1, so since degree of this is less than or equal to n minus 1, and it's an element in the ideal generated by a polynomial of degree n, we must have that this expression gives us the 0 polynomial. But by definition, if a polynomial is a 0 polynomial, then all of its coefficients must be 0. So the zero polynomial by definition is a polynomial such that all coefficients are 0. So this implies that lambda naught equals lambda 1 equals lambda 2 and so on equals 0. All the coefficients must be 0, and this implies that 1 theta n minus 1 is linearly independent, and we've already shown that it spans K, therefore it must actually be a basis for K. Okay. Okay, so let's look at some examples for how this works in practice. Okay, so let's kind of let's try to kind of decipher what this means a little bit. So remark. Okay, so let's try to kind of go back to looking at this field extension we've just constructed of degree equal to the degree of the polynomial, and let's maybe find a better interpretation of it. So let Px, you know what, no, that's okay. So let Px equals C0 plus C1x plus Cn minus 1 xn minus 1 be an irreducible polynomial. In fx, and consider the field K as before. So as we just proved, this is a field extension of f of degree n. So here let's assume, so this actually let's make P actually have degree n. So let's to avoid confusion, so let's actually add a degree n element. 1, 0. Okay, so take some polynomial of degree n, then we get a field extension of degree n. And we get that this is by the above, this is a field extension of f of degree n with basis. So P needs to have degree n, and we need to look at polynomials of degree less than n, and that gives us a basis. So the basis should be 1 theta n minus 1 with theta equals the equivalence class of x. Okay, so notice now that P of theta, this is C0 plus C1 theta plus Cn theta to the n, which is the same as C0 plus C1 x bar plus Cn x bar to the n equals the representative of Px, which is of course 0, as I'm quotienting out by the ideal generated by Px. Okay, so what we've just proven is that the element theta in K, if I sub that back into the polynomial that we started with, then we get 0. Okay, so let's write this out a little bit more precisely. So as we've seen before, we have an inclusion of fields of f into k, where I am denoting the field fx over px by k. So this gives us an inclusion of fields. Okay, so to avoid confusion, let me replace the variable x in the polynomial px by t. So since f and k is an inclusion of fields, we can consider the polynomial pt. So let's just replace x by t. I get a polynomial in f of t. And we can consider this as an element of k t just because the coefficients in f also lie in the bigger field k. Okay, so I can consider the polynomial with coefficients in f. That's a special case of a polynomial with coefficients in k. And then if I do that, so if I consider p of t as a special case of a polynomial with coefficients in k, then we've already seen by the above, so we just saw that if I sub in theta, which is some element in k, into the polynomial pt, which I'm considering as a polynomial with coefficients in k, and we just saw that this equals 0 as an element in k. So in summary, k equals fx quotiented by px is an extension of f such that the polynomial p gains a root in k. So the polynomial pt, which is just a polynomial, the same polynomial as px with the variable x replaced by t to avoid confusion. And then pt might not have any roots in f, or it shouldn't if p is irreducible, but it now has roots in k. So pt might well not have any roots in f, but it has roots in k. So we've constructed a field, given any polynomial, we've constructed some field extension such that the polynomial now has a root in that field extension. So, how do I get rid of that? Okay, there's a root in k. Okay, so compare this to the example we did last time, where we said that the field C was isomorphic to Rx over x squared plus 1. So, well, one way of thinking about C is you want to add into R a element I where I squared equals 1, or equivalently, you want to add into R some element which is a solution to the equation x squared plus 1 equals 0. Okay? So, well, we've just proven that this field, so this is a very special case of the above, which more generally will construct. So just as C can be considered as a field extension of R obtained by quotienting Rx by x squared plus 1 in order to get a solution to x squared plus 1, we just saw that the above lets us do this for any polynomial and lets us extend into a field some, lets us sort of extend any field by adding in solutions to a polynomial of coefficients in that field. Okay. Okay, so in order to apply the previous construction, we need to have some idea of when some polynomial is actually irreducible. So when is a polynomial irreducible? In order to apply the previous construction, I should be able to tell you when a polynomial is irreducible. Okay, so I'm going to give us a criterion that will let us, that we can use to ensure that some polynomial is actually irreducible. Let me introduce some notation. First of all, a polynomial in the ring Rx, R is any ring, is called monic if the leading coefficient is 1. Or in other words, if it has the form px equals x to the n plus cn minus 1, xn minus 1, and so on. So the key point is the leading coefficient, the coefficient in front of the term of highest order, is 1. Second piece of notation, if I is any ideal in the ring R, then we set I squared to be the ideal generated by elements x times y for xy in I. So in other words, it's the smallest ideal containing all elements x times y when x, y are in I. So it contains all products x times y for x, y, and I. And then lastly, let's say that an ideal P in R is called prime if it satisfies a property very similar to prime numbers. So an ideal is called prime if for elements A, B in R, then A, B in the ideal P implies A in P or B in P. So an ideal is called prime if whenever there's some product of elements that lands in P, either the first element lands in P or the second element lands in P. Whenever a product of elements is in the ideal, then one of the two elements is itself already in the ideal. So for instance, if P is a prime element, then it's immediate from the definitions that the ideal generated by P is a prime ideal. Okay, so with these definitions, then we can give a criteria for a monic polynomial to be irreducible. So let me just end today's lecture by writing a criteria due to Eisenstein for when a polynomial in a polynomial ring is irreducible. So let me just write the criterion down now, and then we will discuss this and give examples of it next time. So Eisenstein's criterion. So we should work over integral domains. So let R be an integral domain. And let fx be a monic polynomial. Then suppose, first of all, that there is some prime ideal where all of the coefficients lie in P. So suppose there is a prime ideal where all the coefficients C0 up to Cn minus 1 lie in P. And secondly, suppose that the constant term C0 does not lie in the ideal P squared. Okay, then in this situation, F is irreducible. Okay, so suppose we have some monic polynomial where all of the coefficients lie in some prime ideal, but the constant term does not lie in the square of that prime ideal. Then F must be irreducible. Okay, so that's Eisenstein's criterion. It's very useful. We're going to prove it and then give lots of examples of it next time. Okay, thank you.